Okay, we will start with this materials balance, not metallurgical balance. Metallurgical balance I will come next, because I thought that to understand this, and so this is very important for any activities where you deal with solid or fluid or any kind of your say particulate or anything, like I want to track a pollutant, where it is going from where to where, I need to do and how much of that. So, any system I must do this materials balance. So, what I will do, I will first, because it is a population is from different fields. So, I will show you that how to do the material balance in different type situations. Then next part of this lecture I will deal with metallurgical balances for specifically for mineral processing related applications for that. That is, say suppose I give this example, suppose I have got a flotation plant and I am discharging my effluent to a Damodar river. Now, the environment people come and they say that you are polluting the river, but I can show them that what is the basically the degree of dilution, what will be the net effect of that. But many times what happens that you are throwing it out at the washery site near the Damodar river, but the people who are near say Durgapur, they may be getting affected maybe after 100 kilometers, because there may be reactions and all this. So, how do I know? So, you have to track that and how much of that it is settling, how much of that it is getting transported. So, what is the quantum of that, what is the effect? So, I must need to do the balancing of that. Okay. So, basically the material balance, the philosophy is same what you do it in fluid mechanics, that is your conservation of mass. So, everything has to go somewhere is a simple way to express one of the most fundamental engineering principles. Anywhere where you are doing the material balancing, you know how much it is coming, how much it is going to that circuit, how much is going to that circuit. Maybe you are using a bulk material handling equipment, a set of equipment, this size to this size is going to that section, this size to this size is going to this section. So, how do I design it if I do not know that how much of material I have to transport per unit time. Okay. So, more precisely the law of conservation of mass says that when chemical reactions take place, matter is neither created nor destroyed, exception though in nuclear reactions mass can be converted to energy, but in general we apply this. So, what this concept allows us to do is track materials, suppose pollutants, that is what I say in air, that is I am having air pollution. So, I am throwing dust at here. So, what will be its effect 50 kilometers away from this? So, what I have to need to know, what is the settling velocity of that particle, what is the flow behavior of my air, what kind of your say transport mechanism is there. So, how do I know that I track that particle, how much I have thrown it here and what I am collecting at 50 kilometers away from there. So, then I can say that okay, this is what is happening. So, in doing so, what is the first step? The first step is that it is in a mass balance analysis is to define the particular region in space that is to be analyzed, where I want to know what is the domain. Okay. Now, as examples, the region might include anything from a simple chemical mixing tank, that is whether my mixing is homogeneous or not. How do I know? I have to get the concentration profile, I have to do mass balancing, how much I have fed, how much is there at different your say layers of that, and then it can be to an entire coal fired power plant, a lake, a stretch of stream, anything. So, I must first define the domain. Okay. Now, if I have defined the domain like this with this boundary, then what will happen? The inputs are getting into this system. So, now there could be three situations with this input material. So, suppose I have got a silica particle. So, they are just getting into the system and then just simply going out of this system. Suppose there is no settling, nothing, it is just being transported with my air. But within the system there could be a chemical reaction, there could be a decay. Suppose this is a water body and I am transporting some biodegradable material. So, what will happen? Within that domain there may be a biodegradation, that means when it is going out there could be a decay in between. Then there could be some accumulations inside, some particles settled. So, the input is not equal to output, input is basically a sum of your accumulations plus decay plus output. Okay. So, that is the fundamental equation for material balancing or mass balancing. So, that is basically what I have already discussed. Now, what happens, frequently the equation 1 can be simplified. That means the examples I have given, that there is no accumulation, there is no decay in the system. So, what will happen? Then my input rate is simply is equal to output rate. So, what I have to know, that how much is the residence time of that particle or that system within my boundary. Then I will know that, okay, this material takes this much of time to travel to pass through that domain. So, what will be my rate of your the hazards or whatever you say with that, that is how much is the residence time within that, nothing is getting retained. So, I can simply put these two as 0 and I can say that input rate is equal to output rate. Okay. So, when it can happen, that is when the system has reached a steady state. Okay. So, the steady state means there is no accumulation or there is no decay. So, it is simply input rate is equal to output rate. A second simplification, so of equation 1 results when a substance is conserved within the region in question, meaning that there is no radioactive decay, bacterial decomposition or chemical reaction occurring. That means there is no change with that material. Simply I have got a silicate material, it is just passing through that. So, that means in this case I can say that input rate is equal to output rate. If there is a decay, I have to consider that how much is the decay. If there is an accumulation, I have to also consider that how much is the rate of accumulation. So, it is the rate becomes a very, very important parameter. Examples of substances that are typically modeled as conservative include total dissolved solids in a body of water, like how much is the total dissolved solids. So, there is no further decay, that is dissolved, that is it. So, then heavy metals in soils and carbon dioxide in air. Non-conservative substances would include like radioactive radon gas in a home or decomposing organic waste, because that has got a kinetics with that. So, your rate of decay changes with your time. Okay. So, now let us try to say this, that what happens. So, suppose the simplest system to analyze are those in which steady state is assumed and the substance in question is conservative. In this question, it is the simple, the input rate is equal to output rate. I have given an example, like say suppose there is a stream of river is flowing, okay, and I am interested in this is my boundary condition, like when the river passes by through a village, so that is my domain of basically interest, that I want to know what is the health of my water at that zone, at that territory. Okay. And so suppose there I have got a sewage outfall, that is where I am also throwing some additional pollutant into that river. Okay. Suppose a coal washery, suppose a mineral processing plant, suppose any other industry. Okay. Now, I have said that there is no decay into that, there is no accumulation. Now, I simply write that it is the flow rate is the Qs and the concentration of a particular element is Cs at the stream. Okay. So, that is the river is already carrying some concentration of silicate particles and that has got a flow rate of Qs. Now, in that your sewage outfall, I am also throwing similar type of material, okay, which has got a concentration of Cw, and this is your flow rate Qw. So, what will be the mixture? So, that is I can write that Cs times Qs, that is what is the total volumetric concentration. This is the flow rate and this is the rate of, and actually this is the concentration, multiply that. So, I can get into converted into the mass. So, that is the Qs, Cs into Qs plus Cw into Qw is equal to Cm Qm. Okay. Now, if I ask you or give you a problem, that is where actually I have got some known values and some unknown values, I can calculate them. That is what the specifically this example I am trying to show. Okay. These are very practical examples which you can use it if you are working in different industries dealing with solid fluid or maybe solid or maybe anything, mainly related to your pollution, environment related problems. Even with mineral processing cases, you can apply that. This example I have shown that problem is a stream flowing at 10 meter cube per second has a tributary feeding into it with a flow rate of 5 meter cube per second. Tributary means this is flowing, okay, another one. So, that is a natural stream, and then I have got a basically a tributary to this. The stream's concentration of chlorides upstream of the junction is 20 mg per liter. That means, I have got a chloride into that has got a 20 mg per liter of concentration, and the tributary chloride concentration is 40 mg per liter. Now, when you are disposing that rate chloride, the environment people may come and say that you cannot throw it. Then you can do this calculation and show him that even if I am throwing it, my flow rate is very less. So, ultimately what is the end result? So, whatever product you are getting, whether that is conforming with the water quality or not, allowable chloride limit or not, otherwise you cannot say stop me doing that. So, that is what argument you can put forward with this environment people if you know how to calculate it. Treating chlorides as a conservative substance, that means there is no change, there is no chemical reactions, okay, and assuming complete mixing of the two streams, that means they mix together, they do not, and it is a homogeneous suspension, okay, there is no settling, nothing, in the ideal case of course. Find the downstream chloride concentration. Otherwise, simply by using this, I can do that. It should be basically Qs plus Qw, not Qm. That I later on I realized that there is a typo. It should be Qw. Okay. So, by simply doing that, by using this equation Qm is equal to Qs plus Qw, that is one mass balance, I can do it. That is, what is the volumetric flow rate of input? That is your Qs plus Qw. That is equal to Qm. So, I have got two equations, and another one is by conversion of their masses, that is when I multiply it with their concentration. So, I get two equations. So, Qm is equal to Qs plus Qw and Cm is equal to Cs Qs plus Cw Qw divided by Qm. Now, I can put this value Qm is equal to Qs plus Qw and I can get all the values here and I can solve for Cm. Is it clear? So, I may ask this type of questions in your exam. Okay. So, please practice it because I can make it a little bit tricky also. But this is for, this is a very idealistic case because I am talking about only one stream, one component, but I may have n number of your species and I can have n number of scenarios, but the basic principle remains same. Now, let us take the second case, that is a simple one, that is steady state system with non-conservative pollutants. Okay, like input rate is equal to output rate plus decay rate. I mean there is no accumulation, but there is decay, there is chemical reaction going on. Okay. So, the decay of non-conservative substances is frequently modeled as a first order reaction. So, what I have to do? That all my derivation is based on the assumption that the decay behavior of that component follows a first order reaction kinetics. So, what I have to do? I have to first check that what is the basically kinetics of that decay of my material. Does it really follow first order kinetics? Then only I can use this equation, or otherwise I have to derive my new equation. Okay. If it is not following the first order reaction kinetics, but most of the cases it follows. So, that is, it is assumed that the rate of loss of the substance is proportional to the amount of the substance that is present, that is dC by dt is equal to minus Kc, this minus actually sign given to show that there is a decay, nothing else. So, where K is basically the reaction rate coefficient with dimensions having time, the negative sign implies a loss of substance with time, and C is the pollutant concentration or maybe any element, that what is the concentration of that. Okay. So, to solve this equation we can rearrange the terms, that is dC by C is a minus K dt, and then I can integrate them with the initial at time t is equal to 0, I say that concentration was C is equal to C0, and at time t is equal to infinity I can say that it is C is equal to C infinity, that I will come later, but I say 0 to t if I solve it, that is for t is unknown. So, at concentration at time t the concentration is C, at time 0 C is equal to C0. If I integrate them, we get ln C minus ln C0 is equal to this form, and then initially after all we get C is equal to C0 e to the power minus kT. Okay, no doubt about it, no confusion, it is very simple derivation. Now, so equation 5, that is indicates the rate of change of concentration of the substance. Now, if we assume that the substance is uniformly distributed throughout a volume V, because I got only the concentration of that, and if it is uniformly distributed in V, most of the cases it may not be. So, again the complication will come, but I am only discussing the basic fundamentals of material balancing, okay, but it is only the very elementary thing, it is really elementary knowledge. Then the total amount of a non-conservative substance is thus, so we have to multiply with Cv also. So, dCv by dt is equal to V dC by dt. So, I can write that decay rate is equal to Kcv, because the C is a constant. Okay. So, here I will get the decay rate is equal to Kcv. So, what is the final equation? That input rate is equal to output rate plus Kcv, where V is the volume, C is the concentration, and K is the rate coefficient. Okay. Now, I have not given the solution for this. Okay. I want you to solve it. So, that is what I remember. Yes, I have not given the solution for that. So, you can take note of this problem, that is consider a 10 to the power 6 meter cube lake fed by a polluted stream having a flow rate of 5 meter cube per second. Okay. So, best way to solve all this, that you convert it into a sketch, okay, then it will be easy. And pollution concentration equal to basically 10 mg per liter. There is also a sewage outfall that discharges 0.5 meter cube per second of wastewater having a pollutant concentration of 100 mg per liter. Suppose you are in a mineral processing industry, that is your effluent, you are sending it to a river at this rate. Okay. The stream and sewage waste have a reaction rate coefficient of 0.2 per day. Assuming the pollution is completely mixed in the lake and assuming no evaporation or other water losses or gains, that means it is conserved. Okay. So, find the steady state concentration. So, this is the question. So, this may be your assignment, you can try it, but this type of questions I will definitely ask in your exam. So, practice it. So, this is the second scenario. The third scenario is little bit more complicated than the first two. Okay. So, can I switch over to the next one, or you are taking note of this? Anyway, the PPT you will be given, so you will get this problem, you do not have to take note of this. Okay. Then the third scenario, what happens, that quite often we will be interested in knowing how the concentration will change with time, because we have all assumed that they are all steady state, but if they are not in steady state, they change with time. Okay. When there is a sudden change in the amount of pollutant entering the system, again I am coming back to the mineral processing plant, that you are not throwing the similar amount of material, identical quantity and the concentration of that material into the water body with time. Over a large period of time, they may be having some average value, but if I want to know that today how much I have discharged and what happened to that water body or that particular domain, next day what happened, next day, third day what happened, then what I have to do? I have to consider that also, that is a rate of change also into the equation. So, how do I solve it? Now, this is known as the step function response of the system, from a material balancing point of view, it is called a step function. So, what it is saying, that normally it is being modeled through a basically called the transient analysis through a box model. Like if I boundary, if I domain of interest is basically represented by a box, then you say that incoming flow, that is your basically say suppose the source strength is S and reaction rate constant is defined by K, and this the box volume is V and concentration C, and outgoing you have got a flow rate q and concentration c, then you see that we can basically correlate my this your time interval how it will be varying with some equations. So, in the above figure, the environmental system to be modeled has been drawn as where a box of volume V, that is flow rate q out of the box. So, you know, I have discussed all this, what is that. Then, so from equation 1, what we said, what was the equation 1? That input rate is equal to accumulation rate plus your decay rate plus your output rate. So, now I am interested in knowing accumulation rate, because I already have got formulas for your decay rate, that is KCV. So, but for accumulation rate I need a formula. So, accumulation rate is equal to input rate minus output rate minus decay rate, and I can write, sorry, there is some overlapping of this. So, that is V dC by dt, V is the volume, how much of that, and it is the rate of change of that concentration with time, that is dC by dt, is equal to S, that is the source strength, that is the total rate at which pollutants enter the box, that is what at the previous diagram I have shown, minus QC, Q is the total flow rate out of the box, multiplied by the concentration, C is the concentration in the box and exiting waste stream, and then KCV, K is the reaction rate constant, and remaining thing we have already discussed. Now, how do I solve this? Okay. So, an easy way to find a solution for steady state is simply to set dC by dt is equal to 0. Suppose it is in steady state. Okay. Now, if dC by dt is equal to 0, which yields basically this component is 0. So, I can write C is equal to S by Q plus kV. Okay. So, when it will reach steady state, that I do not know. So, that is time t is equal to infinity. So, there I say that what will be the C infinity. Okay. This is just for solving the equation. We many times we use this type of technique for solving your differential equations. So, which yields C infinity is equal to S by Q plus kV, where C infinity is the concentration in the box at time t is equal to infinity. Now, our concern now, however, is with the concentration before it reaches steady state. So, we have to solve equation 9. So, from what was the equation 9? This was the equation 9. Now, I can put this, that is dC by dt, I can rearrange by putting this value into that, you know, we can get a form that is minus k plus q by v dot C minus S by q plus kV. It is by rearranging I can get that. Now, again how do I solve it? Okay, that is the challenge. So, what we can do it, that is again S by Q plus kV is nothing but C infinity. Okay. So, I can write dC by dt is equal to minus k plus q by v dot C minus C infinity. So, I have simplified it in this form. Now, what we can do, that say suppose C minus C infinity, if I say that is equal to y. So, that is if I say that y is equal to C minus C infinity for my derivation solving. So, then dy by dt I can write is equal to dC by dt, because C infinity is a constant, is not it. So, I can simply write dC by dt. So, equation 12, that is this equation will become dC by dt is equal to minus k plus q by v into dy by dt, sorry, in this case it will be minus k plus q by v into y, correct. That is, I am substituting this C minus C infinity is equal to y. Okay. So, if it is y, so y is equal to C minus C infinity. So, dy by dt is equal to dC by dt. So, here dC by dt I will replace dy by dt, and I can write dy by dt is equal to minus k plus q by v into y. Any doubt? Okay. Which is a differential equation just like the previous equation which we solved. dC by dt is equal to that simple form. So, I can write y0 is equal to y0 e to the power minus k plus q by v into t. Okay. So, where y0 is the value of y at time t is equal to 0. And if C0 is the concentration in the box at time t is equal to 0, then from equation 13 we can write y0 is equal to C0 minus C infinity, which is very easy to know by measurement that what is my initial concentration. That is why we start with initial concentration. I can easily measure that. Okay. So, y0 is equal to C0 minus C infinity. So, by substituting these values into that original equation, so what we can write, C0 minus C infinity is equal to C0 minus C infinity e to the power minus k plus q by v into t, right, agreed. Now, so what we can write, that is what is the C0. So, in this form I can write, if I replace now 0 with t, that at time t what will happen. So, I can write Ct, C is a function of time, that is at what time interval I want to know that. So, Ct is equal to C infinity plus C0 minus C infinity exponential minus k plus q by v into t. Are you deriving it, or am I too fast? Should I slow down the derivations? Because I am not writing it. Normally I prefer to write all these equations when I derive into the board, but here I thought let me give you the typed one. Okay. So, basically I am putting these values now into original equations. So, I get C as a function of time, that is what I am interested in, is equal to C infinity plus that. Now, I want to test that whether my derivation is correct or not. How do I check it? Now, because at t is equal to 0, the it should be C0, Ct should be C0. Now, when t is equal to 0, so what will happen? This exponential function equals to 1. So, what I am left with, C infinity plus C0 minus C infinity, so that is equal to C0. So, it satisfies my initial condition, and that when C is, so and C is equal to C0, and at t is equal to infinity, it should be C is equal to C infinity. How? Now, this exponential function then becomes 0. So, it becomes C is equal to C infinity. So, it satisfies my conditions. So, I can accept that equation. Okay. Now, in a graphically if I plot it, how does it look like? That is, this is the time and this is the concentration of that. So, the C0 could be my initial concentration, and it may take an infinite time where it reaches the C infinity, and that is basically S by Q plus kV, and this is the curve, that is what it is showing, that what is the rate of its decay. Okay. So, that is basically the based on the kinetics of that, and that is what now at any time in between I can know that what is the concentration. So, I want to know, say suppose I put a time that what will be the concentration of this species at that domain, I can go back to that and I can get that value, correct or not? Any doubt? So, let us solve one problem by applying this, okay, where, so do not worry, I am giving the solution, okay, just for practice. Now, say suppose in the previous example, this is very interesting one, say previous example what we said, that we have got a basically flowing river, and there I have got a lake, and there I am discharging some waste material, okay, and there I want to test that with time how much will be the concentration, okay, that is your basically the equilibrium concentration. Now, I say that my environment people came that no, you cannot pollute the lake. I am giving you 15 days time to come back to this. I will, after 15 days I will come back, we will come back and I will take again, we will take a sample. I want to make sure that this pollutant concentration should be less than that, this level. Now, what you will do? You have stopped the sewage outflow, but you have given a time domain. Now, you have to calculate that within 15 days time whether that concentration will go down, because they have already having something. So, what is the rate of decay I must know, and I have to calculate it that whether the 15 days time is good enough, or maybe I have to do something else, otherwise there will be huge penalty. They may stop my productions also. So, that is what this calculation we are going to do, that is how do I check it. Okay. So, that is the precisely the problem. So, the problem is, it is considered that 10 by 10 to the power 6 meter cube lake analyzed in previous example, which under the conditions given was found to have a steady state pollution concentration. So, I am giving you the answer for that question. So, that answer is 3.5 mg per liter. So, if you are in doubt, you please check, that is the answer of that question. Okay. Is 3.5 mg per liter. The pollution is non-conservative with reaction rate constant K is equal to 0.2 per day. It is non-conservative. Suppose the condition of the lake is deemed unacceptable by anyone. Okay. And to solve the problem, it is decided to divert completely the sewage outfall around the lake, eliminating it as a source of pollution. People are saying that because of this sewage outfall, that pollutant concentration has gone up. Now, you have stopped. Now, you want to do a calculation that the incoming stream will still has a flow of Qs is equal to 5 meter cube per second and concentration of Cs is equal to 10 mg per liter. With the sewage outfall removed, the outgoing flow Q is also 5 meter cube per second. Assuming complete mixed conditions, find the concentration of pollution in the lake 1 week after the diversion and find the new final steady state concentration. Now, why should I do it these calculations? Now, this will also tell me that even after, say, suppose how much time it takes to get back to that. So, what is the impact of that? Of course, you are polluting, but are you the only culprit of polluting that lake, or there is some other one also who is polluting the lake also, or whether it is coming from some groundwater contamination? How do I know? So, this calculation will tell you, but here I have to consider your rate of decay of component of that. So, for this situation, so C0 is equal to your initial concentration is, you are going back, that 3.5 mg per liter. The lake volume is already 10 into 10 to the power 6 meter cube, no doubt about that, and Q is equal to Qs, that is 5 meter cube per second multiplied by 3600 second per hour, that is your multiplied by day, basically per day, because the question is for 7 days. Okay. So, what is the strength of this per day, and Cs is equal to 10 mg per liter, that is your mg per meter cube we have to convert, and K is equal to 0.2 per day, that is given. So, what will happen? First I have to calculate the S, that is Qs into Cs. So, I get a value of 43.2 into 10 to the power 8 mg per day. Okay. The steady state concentration can be obtained from equation 10, that is C infinity is equal to S by Q plus Kv. Because I have to know that what is the steady state concentration. By putting this value, I get a value of 1.8 mg per liter. Please practice all this. Okay. Using equation 19, we can find the concentration in the lake 1 week after the drop in pollution from the outfall, that is Ct is equal to C infinity plus that equation. Okay. So, here I can calculate it that C 7 days, we want to know that. So, you give the values, based on that you get a value of 2.1 mg per liter. This is how we can calculate this. Okay. Now, say suppose I can give you this type of problem also, like say suppose in this room we are having 50 people, out of that 10 people are continuously smoking, they smoke say 5 cigarettes per hour, and when you smoke you get some burning sensation, that is because of one chemical comes out that is called HCO, and that is why you are getting some irritation with your eyes. And I say that per cigarette emits this much of HCO. So, per hour you are having this, and your ACs are capable of taking out this at this rate. So, you have to do mass balance, how much is irritating, that whether I will have burning sensation or not. So, whether the number of ACs we have put that is adequate or not, or whether we should request the others not to smoke. Not if nobody is smoking, no problem, but I can say that I can tell them that you can reduce the rate of smoking, that you do not smoke 5 cigarettes per hour, rather if you reduce it to 3 cigarettes per hour, we are comfortable. So, if I want to ask, if I ask you to calculate all this, this will be very it's a good exercise, you know, and this is what you have to do it when you are basically say designing some kind of your public say places like your bar. If you say that I do not allow smoking, people will not come. Okay. So, you have to, and then people who do not smoke, they should not be also having discomfort, otherwise they will not come. So, how do I design your exhaust system, the ventilation system, like your mine ventilation, the similar type of problems we have, and this is by material balancing you can solve, and you can apply all this, basically the fundamentals of this. But in reality what happens, we are talking about only one element here. You can have multiple type of element, some may be having decaying role, some may not be having any change in the reaction. So, you have to go by the matrix method to solve them, that is by node wise, that okay, this transient element, this is having this type of problem, this is having this type of problem, this is having this type of problem. So, and then you have to integrate again. So, you have to first differentiate it, and then say as you do this type of analysis for element wise, and then again you have to integrate it to come back to the real situation, what will be the impact of that. Mostly this type of analysis we do it for environmental analysis, and many a times an environment has become very important for any industry we are talking about. So, this type of calculations will be very useful. Next one I would like to deal with the metallurgical balances, that has got different significance, and if you want we can break now. The tea is there or not, or otherwise we will continue, I do not know. Any question up to this? Is it clear? So, you can comfortably solve problems, okay, we will see.